So here's problem number 2 from the 2012 AB exam. It's a calculator question, and they define the region R to be this region in the first quadrant bounded by the graph of natural log of x. So the natural log of x would be the graph right here. And then also y equals 5 minus x, so that would be this line. So if we want to go ahead and try to find the area of R, as we're asked to do in part A, what we're going to need to decide is how we should slice this region. If you take a vertical slice of this region, and you look at this vertical slice that I draw right here, the top of every vertical slice is on the natural log of x, and the bottom of every vertical slice is on the x-axis. If I draw a vertical slice over here, the top of my vertical slice is now on the line, and the bottom is still on the x-axis. So I have two different types of vertical slices depending on which side of that intersection I'm at. If I want to, I can find the area of this region to the left of this dashed line with that slice, find the area to the right of this dashed line with that slice, or since that's a triangle, 1/2 base times height, and add the two results together. I think if I switch the orientation of my slice, I'm going to be able to do this a lot easier. So I'm going to get rid of these vertical slices, and we'll go ahead and check out what happens with a horizontal slice. If we do a horizontal slice of the region R, no matter where you draw that horizontal slice, the right edge is always on the line. Move that slice up and down in the region, the right edge is always on the line. The left edge is always on the graph of the natural log of x, always over here. So there's only one type of horizontal slice, and that means it's going to be a little bit easier for us to find the area that's desired here. So I'm going to go ahead and treat my horizontal slice as if it were a rectangle. Now the rectangle has a tiny, tiny, tiny height. In the coordinate plane, that would be defined as a tiny difference in y values, so we're going to call that delta y. Now the width of this rectangle is going from this spot in the coordinate plane to this spot in the coordinate plane. That's a horizontal dimension from off that rectangle. It's got to be specified by a difference in x values. I need to specify it so it's positive. So I need to take the bigger x value, and the bigger x value is always the x value that's further to the right. The x value that's further to the right is always on this line. Now, we don't know what that line is given by as an x value. We know what it's given by as a y value. So we'd have to do a little bit of algebra here to figure out what this equals as an x value. Simple algebra, add x, subtract y, and you get that x equals 5 minus y. It's not as simple as switching the x and the y, even though that's what it seems happened here. So the bigger x value is x equals 5 minus y, so I'm going to take the bigger x and then minus the smaller x. Well, the smaller x is always on this graph. Now we know that this graph has a y value is y equals natural log of x. What would this be given as an x value? Well, if we wanted to solve for this x, we're just going to have to exponentiate each side to solve for x. So we're going to get x equals e to the y. So the smaller x value, this equation specified as an x value, is going to be e to the y. And so what would the area of this one slice be? Well, the area of this one slice is going to be approximated by taking 5 minus y minus e to the y, the width of the slice, times the height of the slice, which we just found to be delta y. We want to add together the areas of a bunch of these slices. And what we're going to use as our tool to add together a bunch of these slices areas is going to be a definite integral. So I'm just going to toss the same expression into the integral. The delta y is going to become the dy, telling us what to integrate with respect to. And then we need some limits of integration. Now these limits of integration have to be y values, because we're going to do our integral with respect to y. And they have to be the y values that all slices that we could have taken from within this region range between. Well, the smallest y value, the slice way down here at the bottom of the region, is going to have a y coordinate of 0. So the lower limit of integration 0. The upper limit of integration is whatever the y value is at this intersection. We don't know what that is. We can find that with the calculator. So now it's time to break out the calculator, and we're going to do the rest of the work there. We need to find that upper limit of integration. We need to know this y coordinate. So I'm going to go ahead and I'm going to graph these two functions, 5 minus x and natural log of x. And I'm going to figure out where they intersect. So that intersection, using the intersect feature of the calculator, there's only one intersection, so I should be able to get away with unless, well, I wasn't at a place where the curve was defined that second time I was trying to hit enter. There we go. So that seems reasonable. It seems like that corresponds to the location that they kind of showed to us, this 3.693. I'm going to leave that at 3 digits of accuracy. I'm going to take as much accuracy as I can with this second intersection, because this is the one that I'm actually going to use to stick in as my upper limit of integration. So I'm going to put that value here, and I'm not going to write it all out again. And now I want to figure out what the value of this integral is. So using the calculator's capability to take an integral in the TI-83, that's going to be in the math menu, function integrator. Type in the expression you want to integrate. So I'm looking at 5 minus. Now I know when I hit this variable button it's going to give me an x, so I am kind of switching out these y's for x's right now. As long as you're careful, it's no different than something you've probably done a bunch of times before. So that's going to end the function. I got that last parenthesis there a little prematurely. I need to give the calculator a comma, tell it the variable of integration, another comma, lower limit of integration, another comma, upper limit of integration. I want my answer to have 3 digits of accuracy, so I'm taking that whole entire value that I have up at the top of my screen here, and if I round off this result to 3 digits beyond the decimal, that'll be exactly what the AP exam is going to look for. So I'm looking at 2.98, and I guess this would round to a 6. Now if I truncated that and just left it as 2.985, that would still be okay. But if I just wrote it as 2.98 or 2.99, unfortunately that's not going to get you the last point for the answer to this particular problem.